Section 7.2, geometric sum or series for a finite number of terms. Now for geometric series, or for the sum we get when we add geometric sequences together, we can have either a finite sum or an infinite sum. Alright, so this is a finite sum. This example comes from a previous video. I believe it was part of example 2 when we were writing these in the notation, right? So when we did that, the sigma notation, we wrote this as 5 times -1 to the n minus 1 power, and our series was going from n equals 1 to 11. So I don't know if that looks familiar to you from a previous problem. Okay, so a sub 1 is 5, r is -1/2, first term, common ratio that's multiplied each time, and the number of terms is 11. And again, we found that value in the previous problem. Okay, so now this is our formula. The sum of n number of terms for a geometric sequence is equal to the first term times 1 minus the common ratio to the nth power all over 1 minus the ratio. Let's go ahead and plug this into the formula and see what we get. So the sum of 11 terms is going to be 5 times 1 minus -1/2 to the 11th power, all divided by 1 minus -1/2. Now the fact that it's a -1/2 is really important right here. Well, it's important in this whole problem. I'm going to make this a little narrower because my lines are blending together. So this is an 11. It matters in both places because an odd power, of course, is going to make that negative. And then that negative times that negative will make that overall positive. And then this negative and that negative make this positive. Alright, let me start out with this a little smaller to begin with. Now we just get to do a bunch of math to figure this out. Maybe you have a calculator that will help you with it. So we have 5 times 1 minus, and then -1/2 to the 11th power. Well, to the 10th power was 1 over 1024. So this one would be 1 over 2048. And because it's an odd power and a negative number, that's going to make that negative. So that would give us 5 times 1 plus 1 over 2048. Which we probably need to realize is going to be 5 times 2049 over 2048. Because we can get a common denominator here, turn this little part here into 2048 over, that looks like a 9, 2048. Alright, because 2048 divided by 2048 will be 1, right? So we add that to this, and that's why we get 2049 over 2048. Alright, I've been ignoring the denominator. Let's look at that now. Maybe I'll make it a different color since I've been ignoring it so long. So this is over 1 minus 1/2. That's the same thing as 1 plus 1/2. So that would be the same thing as dividing by 3/2, right? Because 1 plus 1/2 is 3/2. So now we have this thing divided by 3/2. And another way of doing that is to multiply by the reciprocal. So multiply by 2/3. So we're going to have 5 times the reciprocal of 3/2, 2/3, to get rid of our fraction in a fraction. And then we still have our fraction 2048, no, it's 9, sorry. over 2048. So that is 10 thirds times 2049 over 2048, which means we'll have 20,490 over 3 times 2048, which is 6144. That could be the final answer, although I think it reduces a little bit. So going to my handy dandy notes from a previous year. Oh, well, guess what I did? I just left it at this state right here. That's why I left my answer. If you really wanted to simplify this further, I believe both the numerator and denominator will divide by 2. You could use a calculator that actually does fractions for you. So divide that bottom number by 2, and I have 3072, leaving the top number, 24 by 2, as 10,245. So this one ends in 5, this one ends in 2. There's no way that that would reduce further. So I've kind of got this final answer written 3 different ways. They should all be equivalent to the same thing. Let's see what we get if we just find a decimal. That's what I thought, a big ugly decimal, which means leaving a decimal is going to leave it approximate, and we like to leave things exact as much as we possibly can. So there we have it.